Hello everybody, my name is Anton Glinkin, I am application engineer in CDT, and today we will be talking about correct by construction workflow with Constraint Manager. Exactly, we will be talking what is Constraint Manager, why is it important, and what challenges are we trying to solve. And we also look at the basics of DDR just to make sure we have our fundamentals down. And then we will talk about actually creating formulas for these DDR timing relationships. At really high level, constraint management is all about authoring design intent. What I mean by that is your constraints should steer how your PCB design looks, how it performs, and ultimately whether or not it is successful. The challenge is it's actually really difficult to design a successful board on the first pass, because you have to reconcile and balance a variety of different factors that are often conflicting. You have to balance layout solvability with performance and with manufacturability. And that's not easy thing to do. It's not feasible to do by hand. It's not feasible to do in your head, especially when you have an entire design team that needs to be on the same page. This is where sophisticated constraint management tool like Expedition become critical. So you have one place where you can manage all of these different rules. You can create a single source of truth for your entire design team, and what's better is constraint management tool will actually help you to follow the rules that you set, because if you don't follow them, they don't mean nothing. By doing this, you significantly increase your chance of first pass success, and that means that you are reducing the chance of having to respin your board, which costs you time and money. And because time equals money, it means it's double money. So the other large challenge that we deal with in constraint management is just the volume. Working on large designs that have thousands and thousands of nets, it's tremendous work. It takes a lot of time to set up the constraints for all of those nets with intention. And I say with intention because Constraint Manager is a spreadsheet-based tool. It's quite intuitive in my opinion. You can copy and paste, and you can drag cells down, and you can make templates and do all sorts of things to speed up the process of filling these boxes. But the real challenging part is knowing what to put in those fields, and to actually research your interface, to read the data sheets, to understand the limitations of your fabrication process. All of that takes time. The good news is we can take the advantage of IP reuse to help cut down the time. We are often dealing with the same interfaces, things like PCI Express or Ethernet, and sometimes we are dealing even with newer iterations of the same exact board. So why you need to reinvent the wheel, right? We can create a board and constraint the planes, and this is something we're really pushing to our customers. We are either starting from the scratch and building a template from the ground up, or exporting one from the existing design that is already set up well, and then just applying this template to new designs that we create. So it already has certain clearances set up. It already has different interfaces. It already has different schemes for different BGAs, and you can just as a designer take what's relevant and leave the rest. Today we are specifically talking about DDR because, as all of you know, it's something we get a lot of questions about. It's an extremely common interface, but it's also one that is kind of complex. It's constantly evolving, and you can see it on this diagram. The numbers are not too important, but the point is that the periods are getting tighter and tighter, and our constraints have to evolve with the changing interface. And so this can be a little bit daunting, but we talk a little bit about how we can actually set up formulas for a new different examples. And hopefully everybody leaves here with the feeling a little bit more comfortable diving into formulas and Constraint Manager. Okay, so just to recap, I think most people on this call are probably very familiar with DDR. It's dual data rate interface, where we are reading on both rising and falling edges of the clock. And essentially, these are the most fundamental signals you would see. You've got the clock signal, which is primary timing reference, and that's timing your address signals, which determine things like where you are reading data from, and then it's also times your data strokes. That's timing your actual data operations. Depending on which version of DDR you are looking at, you might see this look a little bit different. You might see write clocks or read data strokes, things like that. But fundamentally, this is a basic idea, and anything that's related in this diagram is probably going to have some sort of time relationship associated with it. So with that in mind, how do we actually create formulas? Well, first step to this process is organize your nets in a manner that makes it easy and quick to apply all those different rules. So within Constraint Manager, there are two primary ways to group our nets. You can create net classes and you can create constraint classes. Net classes are largely for grouping nets that have similar physical characteristics. So think trace width or trace impedance. Constraint classes, on the other hand, are good for grouping nets with similar electrical characteristics, or things that you might be grouping that share timing relationships. So generally, we recommend that we make different constraint classes for each of the different interfaces we're dealing with. In this case, you could make a top-level constraint class and call it DDR, and then beneath you would have groups for your byte lanes, your address signals, and your clocks. Inside that, you could further break it down so that under all of those byte lanes, you've got byte lanes 0 through 7. And then, of course, you put in the right signals in the right groups. The nice thing about this is also that you can apply display patterns to each of these different constraint classes. So in this picture on the right, we already color-coded the different groups. You know, the clocks here are yellow, the other signals are orange, and then this enables me to see in a much more visual manner what my signals are doing. So in this picture, since we are for routing, I can very quickly identify where the clocks are, where the address signals are, where the odd and even byte lanes are. And when you look at it from a layout perspective, you know, this actually allows you to optimize your floor planning and even start sketch planning much early in the process. The other really important thing to understand about DDR is the topology that you are using. And that's just, you know, how you are actually going to route these signals. So the most common thing for DDR is probably the flyby topology. And that means that your clock and address signals are actually daisy chained through the DRAMs. The data signals are just going point to point. So those are going directly from FPGA to each DRAM. But the clock signals and the address signals are going to travel from the FPGA to the first DRAM, to the second, to the third, to the fourth, all the way through to a terminating resistor, if you have one. In the tool, we can handle the flyby topology. You can also handle other topologies like T-shape, for example. We can do that. But if you are dealing with the flyby topology, you would need to assign those nets to a custom topology that allows you to set up the netline order and set up the pin pairs. So when you set up the netline order, you are organizing the order of these components basically. And so when you look at your netlines in layout, it all looks correct and you can route your signals in the right order. Pin pairs are a little bit different. These are actual segments of that routing. So in this case, we are breaking down this clock and address signals. So we have different segments going from the FPGA to each DRAM and then between those DRAMs themselves. Now I want to clarify what those pin pairs mean because it can be a little bit confusing with the data signals being routed point to point. So you'll hear me use this terminology, leg X or leg 1, 2, 3, and 4, and those correspond to the pin pairs between FPGA and DRAM 1, 2, 3, and 4. So when I say leg 1, that is corresponding to the pin pair from the FPGA to DRAM 1, and then just a segment that goes directly between those two components. What is confusing is that when I say leg 2, I'm talking about the entire cumulative segment going from the FPGA to DRAM 2, but it has to go through DRAM 1. It's not going directly from the FPGA to that second DRAM, like the strobe signal must be. So you just have to remember that the clock and address signals don't have direct path to those DRAMs. So when we are looking at the pin pair, it's actually getting daisy chained through all of those other components as well. It means that leg 4 consists of leg 3 consists of leg 2 and leg 1, and so on. You understand this. We need to be consecutive. So let's actually look at how that looks like within the tool. So right now we have our constraint classes. We've got a top-level DDR class, and then beneath that some byte lanes, the address signals and the clocks. By default, topology is set to MST, but I'm going to change that to custom for our flyby topology. And that actually propagates down through the hierarchy. So it's very quick to apply changes when you apply them to the top level. Under electrical rules in the left, you can define the net line order from the topology section. And so in this window, you can define from two pairs that define the order. It's a little bit small right now, but if you look in the gray section, it actually looks correct. Right now, we are going from U1, which is FPGA, to U3000, all the way through the terminating resistor. Of course, you can automatically create pin pairs here, but I'm going to walk through the manual process. So if you're looking at a net, you can define pin pairs again under electrical rules. And this looks very similar to a lot of dialogues. You can use the start button to create a new pin pair. And once you have all these new pin pairs, you can just modify the start and end. Start and end pins to be accurate to what you need. So I'm just following the table. We are starting from U1 to U3000, that from FPGA to DRAM 1, from U1 to 3001, from FPGA to DRAM 2, and so on. And then we are also defining a couple between the DRAM, so like U3000 to 3001, and so on and so on and so forth. You can apply this to other nets on your design using templates, but I'm going to hold off that for right now because we will talk about that in a few slides. So once we have all of this set up and you click OK in this dialog, you'll see that we can actually apply separate constraints to each of these pin pairs. So we'll go back and save these changes and then look at the negative flag of our clock. And then here, there is a new row for each of those different pin pairs, meaning we can apply different formulas for each of those segments. Okay, so I mentioned formulas. And I want to talk about why we are pushing formulas specifically. We have our topology set up, that my ordering is good. The pin pairs exist, and now we are ready to define our high-speed rules. Well, there is a couple different ways you can do this. You know, we have min-max lengths, we have match groups, we have hierarchical tolerances, but formulas are by far the most versatile way to create high-speed rules, and here is why. Min-max lengths are excellent if you know the exact placement of the components on your board from the perspective of the layout designer. If you know that your net needs to be 50 mils longer, that's really easy thing to do because you have an absolute value, right? There is no dependencies on any other nets on your design. The other place where you might use this if you run a simulation, maybe in line sim, and you find an absolute maximum value. Let's say the clock can be maximum 3.5 inches before everything breaks down. That's a great thing to put into your max length column, but the challenge is that you do need to know the exact placement of components in order to use min-max lengths effectively when defining timing relationships. So this means that your design cycle is going to get longer because now your layout designer needs to place all of those components, do an initial routing of the board, then go to derive constraints, then go to reroute the board. And if you end up having to change the way things look on your routing, you might have to derive those constraints. So it's not quite flexible. And even with the absolute max lengths, it's worth considering whether you're over-constraining your design. We can see examples when customers who define an absolute max length of 3.5 inches and then they go to specify the same net has to be matched to 2 inches. So it makes no sense. And in this case, max value isn't really doing any harm, but it's also not helping because it's not a limiting factor. So that's just something to think about when you are using min-max lengths. In terms of match groups, these are great when you have some sort of skew requirement within a particular group. So within the byte lanes or within the address signals. The problem is you can only have one match group per net. So if you want to constrain your clock signals and constrain the clock to address skew as well as the clock to strobe skew, you can only do one of these things within match group. You could use hierarchical tolerance for other one, but again, you can only have one per group. And they also don't quite show violations in the same way when you update actuals in the constraint management tool. So you have to be paying a little bit more attention. You actually have to go in the hazard explorer to see some of those issues. And so it just means that there is more work on your end, and ultimately, the goal of using Constraint Manager is to make your life as easy as possible. And the nice thing about formulas is that they are adaptable, reusable, and easy to understand. They are adaptable because they change with your board. you are not using any absolute values because they are relative to other nets. So if nets gets longer or shorter, they still would be applying. They are reusable because you can use variable names within your formulas. Those could be any string. You can put there your name, you can put there your company, anything. And that means that you are not using as many absolute net references. And so if you have different signal net names and different designs, that's fine. You still can use the same formulas, and I would say they are easy to understand. I know that they can be a little bit scary at the first, but often I think the formulas are the way that we picture these constraints in our heads. And it's also the way you'll see a lot of these things listed in datasheets for manufacturers as well. So it's easy to translate that directly to your constraint file. And that's why we will take a look at quick examples. So this example is an AGLX FPGA from Altera. It's DR4. I already colored the constraints directly from the datasheet. And let's talk about this. So in orange, we are looking at the skew matching constraint between the strobe and the clock. And you can see that we have uneven tolerance on both sides. So this is a good candidate for formulas, because if you have an uneven tolerance, that's really the only way to do it. If you use match group and you set 10 picoseconds tolerance, that it's tolerance of 0 to 10 picoseconds in the yellow and the blue. This is like symmetrical. Those are both skew matching requirements within the groups. So within the byte lanes and then within the address groups. And again, you could use formula for this, but you can also use a match group. Match groups are useful for doing skew matching groups within a group, and they can be pretty intuitive. And they just help declutter your formula section if you already have 3 different formulas in there. And then in the green, these are both differential pairs on our design. So we have data strobes and the clock signals. And again, formulas are incredibly versatile. You could use formula, but we do have a separate column for differential pair tolerance exactly for this purpose. So why not use it? Okay, so let's look at how we actually do that. We'll start by setting up these differential pair tolerances, and that is under the differential pair properties view. At least the easiest way to see it, we can navigate to the strobe signal. Okay, we add a 1 picosecond tolerance. It's to strobe 0 that automatically gets rewritten in terms of nanoseconds because it's default unit for this design. And now I can copy, paste that, or in this case just drag that cell down to apply to other strobes. The max differential pair tolerance columns is only available for those differential pairs, so I don't need to worry about accidentally applying this to other signals. But I'm putting the same tolerance for my clock signal, and then we actually go define our clock constraints. So switching to the delays and lengths view, I can start to set up these formulas. To start off, I'm going to define the clock to address skew. So all of these pin pairs that we made earlier here, and I can start to type my variable name. I'll call it variable clock leg 1 plus minus 20 picoseconds for my other pin pairs. For the different legs of this clock, I'm going to modify that variable name like 2, 3, and 4. And then essentially I'm going to be putting these same formulas on the address side, so they are tied in that way. But right here I'm just copying those formulas in for the positive leg of the clock, since I set them up for the negative. And then once we are done with that, we'll set up the clock to strobe skew. So if I want to type a second formula, I can use the pound operator, the hash tag, and then that functionally works as an AND operator in this case and allows me to put new formula inside. It just pulls the net reference one more time. So I'm typing the formula, another variable, we call it clock strobe like 1. And then in this case, I'm giving it a 1 picosecond tolerance. If you remember the table we looked at, the clock strobe skew had an uneven tolerance, and we are just assuming that the clocks is the target signal, meaning that we have the strobe lengths to be modified to match the clock and not the other way around. So if I wanted to, I could give it 0 picosecond tolerance, in which case clock to strobe like 1 would just be exact value of like 1 of the clock, but I'm giving it a 1 picosecond tolerance just to build a little bit more room into design. Sometimes it's easier to put a lot of constraints, but when you make them too tight, it can get really difficult to actually route the board. So sometimes it helps to put in your major constraints and then to work from it there. Okay, so now we'll go handle these same rules on the address and strobe sides. So for address signals, I'm just going to pull out one of those nets. We can do address 0. And I have the same pin pair setup for that already. So I'm going to put the same formulas. The smart thing to do probably would have been to copy this over before I set up these strobe formulas, but since I didn't do that, I'm just rewriting them. You can do it either way. Now I do have a whole lot more address nets, and it would take a lot of time if I wanted to rewrite this over and over again. So I'm just doing a template. I can do that by right-clicking and then creating constraint template. I'll call it address for address and then save it. And when I save it, I can select all of the nets I want to apply to the template. And then in the same way, right-click and apply a template. The benefit of doing this is not only that you can very quickly apply those constraints, but also if need to make any modifications, change the tolerance from 20 to 30 picoseconds. I can do that in one place, and then that will get propagated through over all of the different nets. On the strobe side, I'm going to put it the other half of that formula. So again, referencing the same variable name, we are calling it clock to strobe leg 1. And here is uneven tolerance, plus 85 minus 935 picoseconds. The last thing we are going to do is the constraint the skew within the byte lane. So we can do that using a match group. So I call something like lane 0 mg, and then just assign 3.5 picosecond tolerance like the specification state, and just apply to all of these different nets in this byte lane. Again, we could use template, create template and use if we wanted, and then change it in one place. Here's another example. This is from different chip. This is AMD Versal Adaptive SoC, and this is DDR5 example. Again, this is from datasheet, and what you'll see is they're actually very similar from a constraint standpoint. We have some differential pairs, the clock and the strobe signals, and we can define that differential pair tolerance in the same way. We have our common address control to clock skew, and here the data sheet actually specifies that clock is the target. So in this table, I'm setting up my clock side formulas and giving it a variable name. We are calling it variable clock to address leg x, and then I'm giving it a 1 picosecond tolerance just because it is a target signal. Again, that could be a 0 picosecond if I want to be exact, but in this case, it just gives us a little bit more space for design. On the address side, we are putting the same formula, but with 50 picosecond tolerance. Something I forgot to mention is that you might see the terminology with the TNC, for the differential pairs. They're just true and complement signals, like positive and negative. And then we have our data to strobe formulas. So again, same idea. The strobe specified as a target. We have this variable with a 1 picosecond tolerance, and then the same variable on the data side with a 50 picosecond tolerance. This example does include LBDQ and LBDQS, which are loopback data and loopback strobe signals, and those are used for calibration. But other than that, largely the same clock to strobe skew. Same idea, but this time the strobe is the target, so it has our 1 picosecond tolerance, and then the clock has the plus 1796 and minus 149 picoseconds tolerance at the end. And this is the last example for today. This is LPDDR5. I'm not going to go too much deep since it's very, very similar, but I just want to point out that this looks a little bit scary just because it's a bigger table, but in reality it's just two channels that you can use here. It's channels A and B, so all these constraints are written twice, once for channel A and once for channel B. And if I just pull out these sections that are for channel A, that's what they highlighted in yellow. Again, this is just what we have seen before. We got a few differential pairs. This is our regular clock, and then it's, in this case, you have a write clock and the read data strobe. Basically, instead of having our bidirectional data strobe, we now have two unidirectional signals, the write clock and the read data strobe for the write and read operations respectively. But everything else is the same. You got address to clock skew, command to clock skew, and then some data to strobe to write clock constraints. All right. So with all of that, we have our formula set up, and then next step is in the process is really to route your board and to make sure that your design actually matches the constraint you set. We want to gauge the performance of our board, so it's really important to make sure that you actually have accurate lengths and delay measurements when you are doing this and when you are updating actuals in the Constraint Manager. The first way to do this is to make sure that you are importing the pin package delays or lengths. We have a knowledge-based articles on the support center that goes into detail step-by-step process a little bit more. But essentially, this is information you're getting from your manufacturer, and then you put it into the file in specific format and then just import that in Constraint Manager. You also want to make sure that you set the VL length factor to 1. This is recommended value. By default, it is 0, which means that you are not taking into account any of that z-axis length of VIA. So if you have a really large stack up, you are not taking into account any of the lengths that VIA traveling between layers. We just set it to 0 by default because otherwise we get a lot of questions where people are sort of confused where that the length comes from, because they measure the trace length on the layer and then they don't see the extra length is coming from. But it's just between layers, so vertical. And that's actually something you do on the layout side. So you would do that in layout tool under the setup parameters. And then finally, a small tip, run chhkin command. CHH stands for clean hidden hangers. On the bottom right, you can see screenshots of layout before and after chhkin command. This is just removes small traces that can be hidden inside the paths or any other geometry, but it actually takes it into the lengths calculations since it's trace of the same net. This is a nice way to clean up your design before you send it off. So that basically brings us to the end. Let me summarize what we just talked about. Ultimately, constraint management is all about authoring your design intent. We are trying to create an easy way to map out how you want your board to look, how it should perform, and then to have a tool that helps you follow that intention when you are setting up DDR rules. Formulas are one of the most important things you'll be doing to set up those timing relationships, and they are most versatile. That's not to say that there aren't excellent use cases for your match groups and your min-max lengths and everything in between, but you will probably have to use formulas at some point. So it is a good thing to learn up and understand and to make sure that you are comfortable with it. When you're setting up those DDR rules, you can't forget about the physical side, especially if you're creating the board template. You need to create the physical rules as well. So your schemes for any BGAs or connectors you might need to set up the clearance values to deal with your manufacturing limitations or crosstalk, and then those net classes for impedance matching. So this diagram really quickly summarizes the workflow that we are going through to set up formulas. So just start to making sure that you have really good understanding of the interface you're trying to constrain. Thank you for your time, guys. Always nice.
Thank you for sharing, Anton.
You're welcome. Always nice to hear you here, to see you here, sorry. And that's all for now. See you in a month.
See you.
Bye-bye.
See you. Bye-bye.